Right. So welcome to physics today. It's a beautiful day. We don't need our computers up yet, but we will actually need them at the end of the day today. We're going to do hopefully some lab analysis stuff. We are going to start by explicitly stating and writing down Newton's third law, which we have been talking about for the last 2 days without knowing it. Because that's what I like to do, right? Like we did Newton's first and second law, and we figured it out, and then we said, oh, by the way, this is Newton's first and second law, and now we're going to do Newton's third. And as you see here, I feel very strongly about this, most important law, okay? I think that this one is bigger and better and, the big one of the three. And the reason that I really emphasize that is because, it seems like number one should be the most important, right? And then number two and then number three, not so much. Newton's third law is totally separate from the first and second law, which is, I think, one law. We're going to talk about the third one today. We're going to take a couple notes, kind of talk about what we did yesterday with our pairs, and then we're going to go over the homework, the sheet that you hopefully looked at on Canvas. I don't think any of you came in to get it, but I will give it to you in a minute too. So we've got some time to do that. And then we're going to start the process of doing a lab that we will actually do tomorrow. So we're going to I'm going to introduce you to how to do it so that tomorrow you can just jump in and do it. Okay. Questions before we get started? Okay. You'll need to have some notes out though. So go ahead and pull those notes out. So you're ready to write down. You can write it really big, just like I did. Newton's third and most important law. Now, question for you. How does Miss Carbling feel about just reciting words that have to do with, like Newton's laws or anything else in life? Do we like to just recite things? No. Newton's third and most important law. Newton's third law is the one that people recite most with the least amount of accuracy, I guess. So I really want you to understand it from where it comes from. I'm actually going to move this little picture down for a little bit. We'll talk about it in a minute. We'll come back up here. Oops, let's make this really low. There we go. Oops, no, go away. Here. We'll just make it go away like that. There we go. All right. So can you recall for yourself, what did we do yesterday? So I got here and I handed out those little green pieces of paper. What was that all about? Do you remember? What were we talking about? Force pairs, right? So Newton's third law really has to do with force pairs. Right? Yeah.
I think it was called pairs, the different one.
I did it that way on purpose, right?
Okay.
Yeah, no, I know. I do it that way to keep it in your head, right? Yeah, it's one of those silly little things, right? You're like, oh, wait, pairs, what, pairs? Yeah. You remember from yesterday that we had our forces, and if you didn't notice before, they were in fruit shapes, not peaches and not apples, but they were in pairs, so that you remember and then you know that they are in pairs. So the thing that you want to remember, the keys to Newton's third and most important law, is the first, that forces are an interaction between how many objects? Two objects, always. So a force requires two objects. Okay. Who did I have up here ice dancing with me yesterday or 2 days ago? I don't remember. Yeah, all right, I couldn't remember. Ben was my ice dancing partner. So we were standing here and blah, blah, blah. The music started, and what do we do? Pushed, right? Ben pushed on me and I pushed on Ben. How did the forces compare? They're the same. The magnitude of the force between any two objects is the same. The force of A on B is equal in magnitude to the force of B on A. Okay? The sizes of the force, the size of the force is always the same. Who pushes first?
No one.
No one. And who pushes longer? No one. Same time, right? So the size of the force is always the same. And we'll say the duration of the force is always the same. Now, if you recall yesterday when we had our force pairs and we were talking about that, sometimes our gut feeling tells us that the forces should be different. The biggest example, the number one example that I think about with that is a bug and a car windshield. Okay, so think back to the summer when it was nice and warm, and you were driving at night and you were riding in a car, and a bug just happened to be flying, minding its own business, and just happened to be in the path where your car was going. You with me there? Okay, so the bug is just flying along, minding its own business, just living a happy bug life. All of a sudden, your windshield meets it, right? Does your windshield apply a force to the bug? Indeed, because the bug was traveling this way, and now where's it going? That way, right? Probably a little bit faster. Yeah, absolutely. So the bug accelerates, so we know that there was a force applied. Does the bug apply a force to the car? It does. How do the forces compare? They're the same. That doesn't seem right. Because when you're driving along, just minding your own business, and that bug gets in your way, you don't feel a right? When you're driving along, you don't feel the bugs hitting your car. That would make for a much less pleasant drive. Every time you hit a bug, right? Okay? Why don't you feel it?
Because the bug's mass is so much less.
Bug has a really little mass, which means that even though it's the same force, it has a much bigger acceleration than you do, right? So that's the piece that's important, okay, is that we remember Newton's first and second law that says the acceleration is equal to F net over m. So the greater the mass, the smaller the acceleration. But, and this is the big deal, the force, or the size of the force, is the same. Okay. That is Newton's third law. That's it right there. I struggle because I always debate whether or not to even mention the other version of this law, the one that you've been taught to recite over and over and over. Does anybody know the version of Newton's third law that you've been taught to recite over and over and over throughout your life? For every action, right? So strike this from the record. We're not actually listening to this, right? But for every action, there's an equal and opposite reaction. That's what everybody tells you, right? Have you heard that before? Okay. The reason that I don't like that, I would say even despise that, it really, really makes me unhappy, is number one, what's an action, right? We're talking about forces, okay? And number two, what does the prefix re mean? Reborn or rebound or redo. What does re mean? It means after. Right. Say that louder so that everybody catches that.
They're saying it's after, but we're saying that it's the same time. It is the same time.
Yeah. When I push on Isaac, he pushes on me, not afterwards, but at the very same moment. That's why I hate, despise, and strongly dislike that other version. This is all that Newton's third law is. The size of the forces are the same, the durations are the same. Boom, you're done. Okay? You cannot have one force in isolation. It's not possible. Okay? If I apply a force to the table definitely applies a force to me. Okay? My daughter accidentally walked into the side of a table and bonked her head. Okay? The table applied a force to her head. You with me? Her head also applied a force to the table at the same time. Okay? Same. That's it. Does that make sense? Okay, that's all it is. Okay, good. Yay. Good for us. All right. So I want to look at some pictures here. I was going to print this off and give this to you for homework, but that seemed silly. So we're going to do this together. This is really hard to read, though. So I'm just going to kind of help you see it. Maybe this is a little better. I'm not sure. There are some examples. The first one says, fist hits wall. I hope that doesn't happen to you. That's a really bad choice. Don't do that. Ouch. Fist hits wall. That's two objects, right? Fist and wall. So fist pushes on wall, wall pushes on fist. Okay? That is a force pair. Okay? We'll do the next one together. Head bumps ball. What's the force pair that goes with that? Ball bumps head. Okay? I want you to take a look at the last 1, 2, 3, 4 on this thing. Talk to your table mates. Ben, you're feeling alone. You guys find somebody to talk to. Don't just talk to yourself. Find a friend. Have a conversation real quick. If you can't read it, make it up based on what the picture looks like. Or you can ask me. That works too.
I think the next one is see that.
They're really hard to read though, so it's not, yeah. All right, so let's look at the one labeled B. It says windshield hits bug. That's the example I was given to you before. Windshield hits bug. What's the force pair that goes with that? Bug hits windshield. We talked about that one. C, bat hits ball. Ball hits bat. If you've ever swung a bat and made contact with a ball, which is, not always true for all of us when we're trying to play t-ball, right? Or maybe not t-ball, but softball. Like maybe you don't make contact, but if you do, and the bat hits the ball, you can feel that, can't you? You can feel that the ball hits the bat. Like you can actually, there's something there. Hand touches nose. What's the opposite? What's the force pair? Nose touches hand. Hand pulls flower. What is it? These are easy, right? You got this. The important thing here is that you're just flipping them around, right? You could also say it the way we say it and say the force of the hand on the nose, the force of the nose on the hand, right? Okay, that's what we're going with here. All right. My question for you is, I just wanted to make sure that made sense. My question for you is, did you have a chance to look at this last night? Yes or no? A few of you, maybe? Okay. If you did, awesome. If you didn't, I'm going to give you like 3 or 4 minutes, 3 minutes to look at it and talk to your table mates, okay? I want you to go through these and make sure you've got some solid answers so that you're ready to go so we can have a good conversation. Sound good? Go. All right. So let's take a look. The first one, the tennis ball. A tennis player returns a serve. Of course, the physics student sitting there watching makes the following connection, or contention, excuse me. While the tennis ball is in contact with the tennis racket, the racket exerts a larger force on the tennis ball than the tennis ball does on the racket because the racket has to stop the tennis ball and then reverse its motion. You're sitting next to that physics student, and your comment to that student is what? Do you agree with your friend who also is taking physics? Leanne, you're shaking your head a little bit. You do not agree? No? So you're not going to start a fight about it, but what are you going to say to convince them otherwise? Okay, so you could say that the forces are equal. So what forces are we talking about? So the force of the ball on the racket is equal to the force of the racket on the ball. So let's think about what our friend is going to say, though. The friend says, but wait, the racket has to stop the tennis ball and reverse its motion. How in the world can those forces be the same? What's your response now? Because I agree that that's true, but you got to convince this person. Go, Jordan.
Just mistaking force for acceleration.
Gotcha. So your response is that really what you're looking at, you're focused on the object's acceleration, right? And in this case, is the racket like just flying around randomly, or where is the racket in tennis? Where does the racket exist? Is it being held on to somebody, right? So if you think about it, you've got tennis ball. You can imagine the mass of a tennis ball. And then you can imagine the mass of the racket plus the person.
So the person is with that mass if you add those together.
Indeed.
Because it's behind the ball.
Yes. Yeah, so like person plus racket is going to apply a force to the ball. The ball is going to apply a force to the person plus racket, but who's going to accelerate more? Or which is going to accelerate more, I should say. The tennis ball is, right? Yeah. So we're focused on the object's acceleration. And I want you to write this down because you know what? On Friday, which is in 2 days, is that right? We're going to have a quiz that's going to have some stuff on it that's going to look a lot like this. So I want to make sure that you know this, and not only do you know it, but you know how to write it down. So just, friendly thought for you for the day. Okay, you're focused on the object's acceleration. So your response is also going to be that because the mass of the ball is much smaller than the mass of the racket plus the person, right? That means that the acceleration of the ball is going to be much bigger than the acceleration of the racket and the person, okay, for the same force. The key here is that the acceleration is the thing that we can see. That's the thing that we perceive because we can see that change in motion. And the force is just what causes that change in motion. So far, so good?
Yeah.
Let's keep going. All right, problem number 2 says, accelerating car and boat trailer. Okay. All the trailers shown and cars shown are identical. The boat trailers have different loads. So in each case, the car and the boat trailer accelerate at 1 meter per second squared from rest to the final speed. Rank the difference between the strength of the force the car exerts on the boat trailer and the strength of the force that the trailer exerts on the car while the trailers are accelerating. Did you guys come up with an answer over here? Did you guys come up with an answer?
We were working on it.
Okay, I'm going to give you another second because I want you to get it. We're not going to rely on this one because he's loud. I'm not saying that he's always right. He's just loud. And you know that. I think that's great. Right? I just want to share the fun. So talk about it right now. Talk about it at your table. Don't rely on anybody else. It's you. Talk about it. Figure out what's the right answer.
All of them have the same acceleration. That could start.
Yes. Well, what it says on the probability part of the life. Yeah, what?
Force the car exerts on the boat and the force the trailer exerts on the car.
Because we don't know complications.
All right. Do you feel like you have something? Yeah? Maya, what did you guys say?
You said that the forces are the same, but the accelerations are different.
Say that one more time. I just didn't catch what you said.
The forces are the same, but accelerations are different.
The forces are the same, but the accelerations are different. So for this question, it says rank the difference between the force of the car on the boat and the force of the boat, or the trailer, car on trailer, trailer on car. So the difference means we're going to subtract them, right? So if the car pulls on the trailer with 12 newtons of force, the other one, I just can't remember which one I said, right, is also 12. So what's the difference between 12 and 12? 0. Okay. So in this case, the differences are what? Are they all the same? So should I click, or should I click? Should I mark this one? Yeah, does everybody agree with that? Is there a better answer? They are all 0.
Oh, yeah.
Yeah, that's the better answer. Yeah. So again, like, I don't know, on Friday or at some point in your future, you may have a problem that looks like this that you need to then defend. Because remember, if this is a 4-point problem, how many points is this worth? How many points is the explain your reasoning part worth? You with me there? Right? This is just the like, yeah, great, you got it, but I want to know why. So tell me the why part. Tell me the why part, friends. Who's got it? Go.
In a paired force, the forces have to be equal.
Yeah. So the force of the car on the trailer equals the force of the trailer on the car, right? They are a third law pair. We know that any third law pair, so when you take those two things and you flip them, that's all it is. We know that those two forces have to be equal in magnitude, right? Now, we didn't mention this before, but they're also opposite in direction. That's why they're always talking about the magnitude, the size, because the direction is opposite, always, always, always. But the strength of the forces is always the same. And so then if you subtract them, if you say that the force of the car on the trailer, minus the force of the trailer on the car, well, that's got to be 0, right? Yeah. It does not matter how big they are. It does not matter what their accelerations are. None of that matters. None of that matters. The only thing that matters is that you've got a third law pair. That's it. We doing okay? Okay. One more. Well, 3 more. Hidden as 1. Ha! It's fun how we do that, right? All right. Do you all have answers for these or not quite yet? Do you need another minute? Or do you, because there are 3 of them and there are 3 tables, so I'm going to ask each table to do 1. So would you like another minute to talk about them or no? Yes, please. All right. I'll give you 1 more minute. Go, go, go. Take a look. More stuff to do still today. All right. Do I have a table that would like to volunteer for one of them? You want to do it? Go, Ben. So we're starting with A. Is that okay?
Yeah. Equal to.
Equal to. Let me read the question because I don't remember what it was. Ha-ha. All right. Let's see. 2 identical toy trucks are traveling at different constant speeds about to collide. Oh, no! The trucks are traveling in the same direction during the collision. The magnitude of the force exerted on A by B is greater than, equal to, or less than B on A. And you said equal to?
Yep.
Okay. And why did you say so? Boom. Make sense? F of B on A equals F of A on B. Done. Sweet. All right. Question number B. Who's got B? Stella, you got it? Go. Same. So we got collision. What's the difference in this collision between A and B? So this one, we had like a rear end collision, and this one's like a head on collision. But it doesn't matter. It doesn't matter what directions they're moving at all. It just says the magnitude of the force on A by B, on B by A, equal. Boom. So.
Could we explain it? So if they're going at constant speeds,
Yeah.
then that means their accelerations are 0, right?
To start.
To start.
Yes. As soon as they interact, though,
That's different.
they're going to change, right? Think about this one, the head-on collision, right? This one's moving at 3 meters per second. This one's moving at 4 meters per second. When they collide, this one's not going to keep moving at 4 meters per second.
So you can't explain it like if you do mass times acceleration, that F net is going to be 0.
No, you can't. No, F net is 0 until the collision.
Okay.
Collision means forces. Yeah, that's a good question though. Yeah. So the extreme example is that a collision with nothing does give you an F net of 0. But a collision with something then gives you some other F net. Yeah. Yeah. All right, my friends. Who am I going to pick on here? Monse, you got this one?
We're really confused on the last one.
On part C? Okay, let's take a look at it together, okay? All right. So question C says the trucks are traveling in the same direction. So this looks like it's the same as part A, I think. During the collision, oh, this one's different, isn't it? This one is different. It says, will the acceleration of truck A be greater than, less than, or equal to the acceleration of truck B? That's different. They're throwing something different at us. We do know from Newton's first and second law that A is equal to F net over M, right? So if we write this out, we could say that the acceleration for car A is going to be equal to the force of B on A divided by the mass of A. Does that make sense to you, or did I just totally mess you up?
No, that makes sense.
Is that okay? The acceleration of A is equal to the force of B, because that's the only force acting, divided by the mass of A, okay? And then we can say the acceleration for car B is equal to the force of A on B divided by the mass of B. Is that okay also? Now, you don't have to have this all written out to get the answer, but I just want to, it's a nice way to kind of say it. So, we know that this force is the same as this force because you told me that in part A, right? Those forces are the same. So the accelerations are going to be then dependent on the masses. How do the masses of the carts compare? Do we have any idea?
Two identical trolley trucks.
It says that they're identical. What does that mean about their masses?
Would they be the same height?
It seems like identical would imply that they're the same, right? Yeah. So that means that we know F of B on A equals F of A on B. And we know that MA equals MB. So that means that this equals this. So if you have the tops that are the same and the bottoms that are the same, what is that going to tell you about the answers? Same accelerations.
Is that a mathematical property?
I mean, I'm sure it is. Yeah, the identity property, right? Like if two things equal the same thing, then they equal each other. I think that's the identity property, isn't it? I don't remember. I used to have them memorized because I used to teach it, but I don't remember. Answer there is the what? What's the right answer then? Equal. Now, if the cars have different masses, like you might see, I don't know, on Friday or something like that, right? Then you would have to figure out if car A or truck A or whatever kind of vehicle this is, vehicle A has more mass, then which one's going to have a bigger acceleration? Does that make sense? Bigger mass, smaller acceleration. Smaller mass, bigger acceleration. You okay? Sweet. All right. Yay for us. We understand physics. So we're going to have a quiz on Friday over this stuff. Just heads up on that. What I'd like you to do right now is to go get your computer, turn it on, get ready, because we're going to jump in and do a little bit of kind of the groundwork for the lab that we're going to start tomorrow. Okay? Do you have a charger? Or does anybody have a charger that we could share?
I do.
Excellent. There's some